In this video, we are going to find all prime numbers p such that p cubed minus 4p plus 9 is a perfect square. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. A more precise way to write this equation would be to say p cubed minus 4p plus 9 equals x squared some non-negative integer x. Then I'll take mod p on both sides so that we have x squared is congruent to 9 mod p. And from this, we can say that x plus 3 times x minus 3 is congruent to 0 mod p, and therefore x is either 3 or minus 3 mod p. So to rewrite this as an inequality, I'll let x equals k times p plus or minus 3, some integer k. Then I can put this back into the equation above and say that kp plus or minus 3 all squared is equal to p cubed minus 4p plus 9. And also we can expand the left side, and we have k squared p squared plus or minus 6kp plus 9 is equal to p cubed minus 4p plus 9. So p cubed minus k squared p squared plus, I would say it's not actually plus, but I can say plus or minus 6k minus 4. Put it this way, plus or minus 6k minus 4 times p equals 0. And of course, a prime cannot be 0, so p squared minus k squared p plus or minus 6k minus 4 is equal to 0. So I can conclude that 6k plus or minus 4 is a multiple of p, like this. Now, if p is even, then of course it's fine, because 2 must divide 6k plus or minus 4. The coefficients are all even. However, if p is odd, not even, which is the vast majority of the cases, then I can even divide the multiple by 2, so as to say p divides 3k plus or minus 2, and make it as a bound by saying p is at most 3k plus 2. So now we know that k is at least p minus 2 over 3, and so that means p times k minus 3, which is one of the possible cases for x, would be at least p times p minus 2 all divided by 3 minus 3, which equals to p squared minus 2p minus 9 all divided by 3. And we know that this pk minus 3 would be always less than or equal to x. So given an equation of p and x, we now have established an inequality, again, about p and x. So we have x to be at least p squared minus 2p minus 9 all divided by 3. From this inequality, we might want to square both sides, because all we know about x is that x squared equals p cubed minus 4p plus 9, and we know nothing about x itself. But if one side is positive and the other side is negative, then just squaring both sides directly would create some kind of some of the cases that we actually do not want to consider. So why don't we only focus on the cases which makes p squared minus 2p minus 9 all divided by 3 a positive number. Indeed, if I rewrite this as p minus 1 all squared minus 10 all divided by 3, then this expression will be positive for all primes starting from 5. So we can split into two cases. If p is at most 5, then I can square both sides of this inequality. I can say x squared is at least p squared minus 2p minus 9 all divided by 3 all squared, and x squared by definition is p cubed minus 4p plus 9, and that's at least p to the power 4 minus 4p cubed minus 14p squared plus 36p plus 81 all divided by 9. Then simplifying, we have p to the power 4 minus 13p cubed minus 14p squared plus 72p is less than or equal to 0. And of course p is positive because p is a prime number, so we can say p cubed minus 13p squared minus 14p plus 72 is at most 0. Notice that this cube egg can be factorized as p minus 2 times p squared minus 11p minus 36. So solving, we know p is at most 11 minus square root of 265 all divided by 2, or p is between 2 and 11 plus square root of 265 all divided by 2. So from this inequality, we can just ignore the other one because that means p is negative. We can quickly reject it. So from the highlighted inequality, we know p is either 2, 3, 5, 7, 11, or I can even take 13 as well. So when we restricted the inequality into cases where p is at least 5, we have these solutions. So why not we just check all of them all together. When p is 2, then x squared, which is just p cubed minus 4p plus 9, would be 9. So it's a perfect square. We're good. When p equals 3, we have x squared to be equal to 24, not a perfect square. When p is 7, then x squared is 343 minus 28 plus 9, 324, perfect squared. Take. When p is 11, then x squared equals 1331 minus 44 plus 9, 1296. A perfect squared is 36 squared. And finally, when p equals 13, is 2197 minus 52 plus 9, 2154, not a perfect square. So altogether, our answers can be 2, 7, or 11. So this is the final answer. Please feel free to share ideas in the comments. Thank you for watching. See you next time.